Everyone, welcome to my YouTube channel. So here today we are going to be looking at what we call the Bohr model. So what is the Bohr model all about? So it tries to explain why electrons are fixed here. We know that positives and negatives are attracted to each other, but why are electrons not going to go there? That is number one. And also, if electrons are constantly able to more like revolve around like that, they are constantly moving, that means to say they are using kinetic energy. And if they are using kinetic energy, why is it that their energy does not run out? They will continue to spin and spin and spin. So that is what the Bohr model tries to explain. So firstly, one thing that we need to know is that the electron position is quantized, meaning to say there are specific positions in which an electron must be. So that means to say an electron might be here, might be here, might be here, might be here, but an electron will never be here. It can be in another energy level like that, or rather a shell. It can be there, it can be there, it can be there, it can be there, as long as it's a shell. So that is what we call the energy, or rather the shells are quantized. So they are quantized. So that is what we mean by electrons are quantized. They can never be in between like that. So now we get to realize that according to the Bohr model, an electron will jump from one energy level to the next with respect to what is available. So for example, in this context, what is important is this. So if you have something like this, remembering our photoelectric effect, so let's say if an atom absorbs energy, so this is what happens. So if energy is added to the atom, let's say if that energy is absorbed, an electron will move from one energy level to the next because it has got more energy. Why does it move? So this is simply because each energy level has got quantized energy, meaning to say it has got specific amount of energy in each energy level. So therefore, since the energy is quantized, it means to say when there is a gain in the electron, that means when there is a gain in the energy, an electron will jump from one energy level to the next. So each and every time, so a photon or any energy is absorbed, an electron will be able to jump to the next energy level. It won't be in between, but it will jump to specific energy levels. So that means to say if it is here, it will jump, let's say, to there. So what would determine this jump is the amount of energy that the electron has gained. If the energy gained is actually the difference between the two shells, it simply means to say the electron will move to jump to the shell with that energy difference. So let's say, for example, in this energy level, the energy is 20 joules, then here it is 40 joules, then here it is, let's say it is 60 joules. It means to say here the electrons that will be here will be having an energy of 20 joules. Then also, if there is a gain of 20 joules again, it means to say there will be an addition of 40. It means to say an electron will jump at 40 like that. But if there was a gain in 40 joules here, it means to say it will jump there, so that the energy difference is actually the jump. So that is what we mean by the energy is quantized, the jump is quantized. Likewise, the opposite is the case. If there is a, however, so if it loses energy, it will be able to step down. It's more like to step down. Now when it steps down, what happens to the energy? So some energy has to be released as a photon. So a photon is a particle of light like that. So as it releases energy, it means to say if here it has 60 joules, as it releases energy, 40 joules will be released in order for it to go there. So that is what we mean by the quantized energy. So this is true as long as you are looking at the Bohr model. So to explain this, we have now what we refer to as a line spectrum. So the line spectrum explains why some gases such as hydrogen is able to produce only discrete colors. That simply means to say some colors, not all of the colors, like the continuous spectrum. So let's differentiate something. So the line spectrum. Now if you look at the continuous spectrum, so when we look at white light, this is what happens. So white light is able to be split into its various components as seen in the rainbow. All the colors are there: violet, indigo, the blue color, green, yellow, orange, red. However, to prove that quantized energy is true, we are going to look at the line spectrum. So when hydrogen is more like heated, it releases energy like that, and this light, or rather this type of light, is split in two lines, not like the continuous spectrum that we have. So these line spectrum are seen as different wavelengths, which are the 656, we have 486, 434, and 410, the common wavelengths in nanometers. So this is the light that is visible. Now you can see that it is not continuous, which tells you that the energy is specific like that. So the energy is very, very much specific. Now the hydrogen is split into the spectral series. So these series, which are very examinable, are the Lyman series, the Balmer series, the Paschen series, the Brasket series, and also the P-Fund. So now I've made something that is very simple for you to remember. So we are going to just say, Lyman's, Bohr, past, Brack's, foot, like that. So we have the Lyman series, the Balmer series, we have the Paschen series, the Brasket series, and we also have the P-Fund series. So now what are they? So this simply refers to the drop. So we have the drop to 1, the drop to 2, the drop to 3, the drop to 4, the drop to 5. So as you can see, if we have the drop, if at any energy level if it drops to number 1, then that simply means to say that is what we are going to call the Lyman series, and this is the one that produces ultraviolet radiation. So the ultraviolet radiation is very high energy because it is even closer to the nucleus like that. Then we have the Balmer series. As long as we have the Balmer series, it is the second. So as you can see, second the drop, wherever it was, it might be from the third energy level to the second, fourth to the second, fifth to the second, sixth. As long as we have that is the Balmer series, and the Balmer series is responsible for producing the visible type of light. Then the last are the infrared type of radiation. So the Paschen series is from any energy level to number 3. The Brasket series is from any energy level to number 4. P-Fund is energy level number 5. So that those are the drops. So you can use this simple mnemonic. So Lyman's, Bohr, Brack's, foot. So that is what you can be able to use. So now this shows the energy. Now one thing that you need to know is that there can be an infinite number of electrons. Let me increase this. So as you can see, there can be an infinite number of electron shells. So these lines that you see are these shells like this. Now you cannot manage to draw shells like this, so that's why they are put in lines like that. So as you can see, this is energy level number 1, like that. Number 2, there is quite a big gap. Number 3, there is quite a big gap like that. Then we have number 4, number 5, like that. They continue like that. The more you go, the more they increase. So there could be an infinite number of distance over a finite amount of, an infinite number of shells over a finite distance. So that simply means to say there could be as many shells, but over a finite distance, meaning a distance that can be measured. So whichever distance, it can be this one, there can be an infinite number of shells like that. So now the more you move away from the nucleus, which is somewhere here, the more the space between the energy levels reduces. As you can see, the energy level distance reduces like that. So that's why there could be an infinite number of shells, but over a finite distance like that. So with that said, it means to say, if we have something like this, we have, let's say, there is a drop from energy level number 4 to energy level number 2. The energy, if there is a drop, it means to say a photon has to be released. Remember, a photon is released each and every time an electron moves from one energy level to another. So energy has to be released. So if let's say it moves from energy level number 3 to number 1, because number 1 there's a very high distance, that means to say it will produce a very high amount of energy, as compared to, it could even be at energy level, let's say this is number 4, 5, 6, 7, 8. It could be number 8, it comes to number, let's say 2. You might find that from 8 to number 2, it might produce less energy as compared to just let's say number 4 to number 1, because of the space like that. So that is the behavior. So that is how you can know them. We have the Lyman, which is the ultraviolet, the Balmer series, which has to do with the visible lights, the Paschen series, which has to do with the infrared, as well as these others, the P-fund and others, and the bracket. So you can know those in that simple manner. So this was what we said. So we have, if an electron moves to one energy level to the other, it means to say energy was absorbed. If an electron moves from one energy level that is higher in energy to a lower energy level, it means to say energy has to be released. The energy released or gained is equivalent to the amount of energy difference between the two energy levels, which I have explained. So with that said, let's move on to some calculations. So to calculate this energy change, there are two formulas that are used, or rather to find the wavelength. So let's say if you are asked to find the wavelength. So to find the wavelength, you can use two formulas. Firstly, some formulas that we know, we have the speed of light is equal to the frequency times the wavelength. So the wavelength has got this symbol. Frequency, according to this topic, has got this symbol of nu. So this is the symbol for frequency. So you can just name, this is the frequency, then this is the wavelength, then this is the speed of light. speed of light. So the speed of light in a vacuum. So now when we look at this change, there are two formulas that are used to calculate the wavelength. So it can be 1 over the wavelength is equal to, we have 1 as if you're just saying a number, then you will say 0.9678, just follow the numbers like that. Then we have 1 over n1 squared. n1 is the initial, minus 1 over n2 squared. Then we are going to say this is in centimeter to the power negative 1, like that. So there is this, or there is the change in energy can be calculated as being equal to, we have the Planck's constant times the frequency. So this is the amount of energy. So in order to, and you should know some of the things, Planck's constant is equal to 6.626 times 10 to the power negative 34. So this is the constant for Planck's constant. So now let's answer this question using the two methods and see. So we have been given, calculate the wavelength of a proton in nanometers emitted during a transmission from n initial is equal to 5 to n final is equal to 2. State in the hydrogen atom and identify the spectral line series. So we are going to use, let's use this one first. So we have 1 over the lambda is equal to 109,678. Then we have 1 over n1 initial squared minus 1 over n2 initial squared. Now remember the what's this? The wavelength can never be negative, and if we look at n1 already is 5, and 1 over 5 is less than 1 over 2, because we are looking at 1 over 2. So if you subtract these, you are going to get a negative. So what you can just quickly do is you can just interchange these to give you a positive answer. So you put your n final squared, which is your n2, over, which is the last position, over the n1 squared, like that. So yeah, so just to make it positive, so we have 1 over the lambda should be equal to 109,678. Then you have the final position it has reached is a 2. So you are going to say 1 over the 2 squared minus 1 over the value, which is our 5. So this 5 squared, like that. We have the centimeter to the power negative 1. So we do our calculation. 1 over the lambda should be equal to, we have our 109,678. Then we have 1 over 4 minus 1. This is 1 divided by 4. 2 squared is 4. 1 over 5 squared is 25, like that. Then we have the centimeter to the power negative 1, like that. So then what we are going to have is, let's subtract. So we have 1 over the wavelength, 0. We have this. So when we subtract here, what we are going to get is, so we can just do it, 1 divided by 4 is 0.25 minus our 1 divided by 25. This is going to give us a value of 0.21, like that. We have the centimeter to the power negative 1, like that. So what we are going to get is, we have this value times 109,678, like that. So we have a value of 232, like that. So we have, this is in centimeter to the power negative 1, 1 over lambda. Now here, what you're going to do is you're going to raise everything to the power negative 1 on the calculator. So you put that in brackets and press your power to the power negative 1. So what happens if you put to the power negative 1? This goes up. So this lambda goes up. We are going to have lambda is equal to 4.34 0.17 times 10, it is giving us 10 to the power negative 5 centimeters, like that. So if that's the case, what we are they want nanometers. Now what you just need to know is, without wasting time, 10 to the power negative 7 centimeters is equal to 1 nanometer, like that. Then if you look at your 10 raised to the power negative 9 meters, remember this 10 to the power negative 9 is nano, then meter. So if you have any of these, so since we have the centimeters there, we are just going to move the decimal points twice, like that, so that we have the lambda is equal to 434.17 times 10. Now each and every time you move your decimal points to the right, it simply means to say you are subtracting. So since you have moved it twice, there is a gain in terms of the negativity by 2 times. So it will be negative 7 since you have moved it twice here, there. So this is what we have, centimeters, like that. So we have lambda is equal to 434.17 times 10 to the power negative 7 centimeters. So this gives us a lambda of 434.17. This one you can put nanometers, like that. So this is how we solve that one. Alternatively, using the energy, we have another formula which we are going to call, we have this formula which we are going to have, the change in energy should be equal to, we have the Rydberg's constant. So others will put negative, but if you don't put negative, you will just say 1 over the initial, which is number 1, minus 1 over number 2 squared, like that. Then this is the formula for energy. So now, using this formula, you can find the energy. Then using another formula for energy, remember we said energy is equivalent to, we have this. You can use this now to find the wavelength. So let's do this one as well. So if you put a negative to the Rydberg's constant, it means to say these two have to be interchanged. So now in this case, if we do that, we are just going to say n1 minus 1 over n2 squared. So the change in the energy, you will say, should be equal to the Rydberg's constant, which is equal to, so for this one it is 2.18 times 10. So we have 18 to the power negative 18, like that. So this is the Rydberg's constant, 2.18, and times 10, you will just repeat the 18, now it will be negative. So we have 1 over, the initial position was 5, so 5 squared minus 1 over 2 squared, like that. So initial 5, final 2. So we are going to have 2.18 times 10 to the power negative 18 joules, like that. Then when we do that, we are going to have 1 over 25 minus 1 over 4. So when we subtract, we are going to have our, so we have 2.18 times 10 to the power negative 18 joules. Then we have negative 0.21, like that. So it is, this is the change in the energy. So change in the energy. So when we multiply this, so this was the reason why I interchanged them for wavelength, because wavelength can never be negative, but the change of energy can be negative. Why can it be a negative? If energy has been released, you have to add a negative because energy is lost. So we are going to have 2.18 times 10 to the power negative 18. Then we multiply by 0.21. We are going to have a negative 4.578 times 10 to the power negative 19, like that, joules. So this is the energy that is lost. Now, with that said, we know that we said this, remember, the energy can also be found by saying the Planck's constant times the wavelength, not the wavelength, times the frequency. So that's the symbol for frequency right there. So with that said, we also know that we don't know the frequency, but we also know that the speed of sound is equal to the wavelength times the frequency, like that, if you remember this formula. So we can get this, and let's make the frequency the subject of a formula. So we are going to divide this, divide that. So we are going to have the frequency should be equal to the speed of light over that. So we are going to get this and substitute there. So let's substitute here. So when we substitute, what we are going to get is we are going to get the change of energy, or rather just the energy for this one should be equal to, we have the Planck's constant times, where there is this, we are going to put C over the wavelength, like that. Now one thing that you need to know is that for this one, the wavelength it will give you, it will be in meters. So we are going to say, let's make the wavelength the subject of a formula. So this goes there. We are going to have our energy times the lambda should be equal to hc, like that. We divide over the energy, so this will be our formula for the wavelength, which will be in meters. So to forget this arrangement, you can just spell the word chemistry. We know that this is in chemistry, so the last letter has to be down. So this is the formula for wavelength when you make everything the subject of a formula. So with that said, we are going to have the wavelength should be equal to the Planck's constant. Remember, Planck's constant is equal to 6.626 times 10 to the power negative 34, like that, times our C is the speed of light, which is 3 times 10 to the power 8 meters per second. So that's why even the wavelength is in meters per second, over the energy, which was in joules. So the energy we calculated was this value. Let me just lift it. So this value is the energy that we are going to put at the bottom. So this one, you just need to be very careful with how you handle the calculation. So we are going to put it there, but omit the negative. So we are because wavelength cannot be negative. So we are going to have this, our 6.626 times 10 to the power negative 34. Then we multiply times 3 times 10 to the power 8. This gives us a 1.9878 times 10 to the power negative 25. Negative 25 times 10 to the power negative 25. Then we divide this over our 4.578 times 10 to the power negative 19 joules. So we have a value that is equivalent to, we divide our value. So what we're going to get is, if you divide this, so remember how you press in your calculator, on your calculator, you put these in brackets, you divide, divided by, you put these in brackets, then you're going to say enter everything to the power that, then divide like that. So the answer we are getting is a 4.342 times our 10 to the power negative 7. Now this is meters. So if it was centimeters, we could have said nanometers, but since it's meters, you need 10 to the power negative 9 meters is equal to, we know that 10 to the power negative 9 is nanometer. So that's how come 1 nanometer is equal to this much. So we are going to move the decimal point 2 times. Why 2 times? So that this can change into a 9. So we have the wavelength is equal to 434.2 times 10. So each and every time you move this side, it will be an addition of a negative. So we are going to say finally the wavelength is equal to 434.2 nanometers. So whichever method you use, you're going to arrive at the same answer. Let's look at this other one. Let's just finish the last part, which was saying that and identify the spectral line series. So the spectral line series. This one is the Balmer series. Remember, we are looking at number 2. As long as there is a drop to number 2, that's the Balmer series. Number 1, Lyman series. Number 3. So what did we say? We said Lyman's, Bohr, past. So it's Paschen, Brasket, which is number 4, foot, which is number 5, like that. So that is an easy way of remembering that. Let's try out this one again. Another one. So we have 1 over the wavelength should be equal to. So we are determining the wavelength of light when the electron in an hydrogen atom undergoes transition from energy level number 4 to number 2. So we are going to have 1 over this. Then we have 1096. So we are beginning 6, 7, 8, like that. Then we are going to have our 1 over n final squared. Why final? Because we don't want it to be negative. If there's a drop, wavelength can never be negative. 1 over initial, or number 1 squared, like that. So centimeters, -1. Don't forget that. So we have 1 over this should be equal to 1, like this. Then we have the 1 over the final is 2 squared minus 1 over the initial is that squared. Then we have centimeter to the power -1. So we are going to have 1 over the wavelength should be equal to 1, 0, like that. Then we have 1 over, this will be 1 over 4 minus 1 over, this will be 1 over 16, like that. So we are going to have, so this is centimeter to the power -1. So we have 1 over this should be equal to 1,09678. So when we subtract 1 divided by 4, just be careful on your subtraction, minus our 1 divided by 16, this will give us a value of 0.1875 centimeters to the power -1. So 1 over this should be equal to, we are going to get a, so when we multiply 1,09678, we are going to get something that is equivalent to a 2564.625. Then we are going to apply an inverse to both things. So that's how come the inverse on the centimeter will disappear. This will go up. So we are going to have the wavelength should be equal to, we have this value to the power -1. This will give us a 4.863. Then we have centimeters times 10 to the power -5 centimeters. So now we are going to move it 2 times so that we can have the wavelength is equal to 486.3 in times 10 to the power. We have moved it twice, so there will be an addition. So -2, -5 minus 2, this will be -7. So that's why we are writing a -7 there. So we have -7 centimeters. So 10 to the power -7 centimeters is equal to 1 nanometer. Don't forget 10 to the power -9 meter. 10 to the power -9 is a nano, so we are going the nanometer. So in this case, if we have the centimeters there, we are going to say nanometers. So we have this should be equal to 486.3 nanometers. Let's try out the alternative. Alternatively, we are going to say the energy should be equal to the Rydberg's constant. Here you begin with the initial squared minus 1 over n final squared. If you want, you can just add a negative and begin with a final. But if you do this, if you begin with the initial, you don't need to put negative to the Rydberg's constant. So the change in the energy will be equal to, we have Rydberg's constant, remember, 2.18 times 10 to the power negative 18. We are just repeating this number. 1 over the initial position is number 4 squared minus 1 over the final. It is dropping at 2 like that. So we have the jaw there. So we have the change in energy should be equal to 2.18 times 10 to the power negative 18. 1 over 4 squared is 16 minus 1 over 4 like that. So we are going to have the change in the energy will be equal to, we have 2.18 times 10 to the power negative 18 times, we have 1 divided by 16, then minus 1 divided by 4. This will give us a value of negative 0.1875. So the change in the energy, it's giving us negative. It is change, it is not just energy. So that means to say that amount of energy is released. So we are going to have 0.1875 times 2.18 times 10 to the power negative 18. So this is going to give us 4.0875 times 10 to the power negative 19 joules like that. So this is the energy. So remember the formula that we made, the subject of the formula, we just spelled the word chemistry. So it is chemistry. So this was negative. But for this one, we're just going to use the energy. So because wavelength cannot be negative. So we are going to have the speed of light is 3 times 10 to the power 8 times the meters per second times the Planck's constant, which is 6.626 times 10 to the power negative 34 over, we have the energy, which we found to be 4.0875 times 10 to the power negative 19. Our joules there. So we are going to have on top 3 times 10 to the power 8 is going to give us that times 6.626 times 10 to the power negative 34. Just be careful with the numbers. Finish on top. So on top we have 1.9878 times 10 to the power negative 25 over, we have 4.0875 times 10 to the power negative 19. So we are going to have when we divide this, we are going to have 4.0875 times 10 to the power negative 19. This is going to give us a value of 4.863 we have times 10 to the power negative 7. Now this gives you in meters. So you will move 2 times for meters. You will have your wavelength to be equal to 486.3 times 10. So it will change to times 10 to the power negative 9 meters. So this will give us 486.3. Where there is 10 to the power negative 9, that will be nano. Then we have the meter like that. So that's how we get those values. So if we have the energy difference in joules between N1 and N5, which is the principal energy level of an hydrogenic atom. So to find the energy difference, we have the energy, remember it should be equal to, we have the Rydberg's constant, 1 over N1 squared minus 1 over N2 squared, like that. So we are going to have the change in the energy will be equal to, we have Rydberg's constant 2.18 times 10 to the power negative 18. Then we have 1 over from 1 squared minus 5 squared. Though this question is not telling you, it's not saying which one is they are just saying the energy difference, but we don't know whether it's moving up or down. So the energy difference will be equal to, we are going to put 2.18 times 10 to the power negative 18. Then we have 1 over 1, or rather just 1 there. So 1 minus 1 over 25. This will give us a value of, so we write 2.18 times 10 to the power negative 18. Then we have our 1 minus our 1 divided by 25. This will give us a value of 0.96. So the difference in the energy for this one is, it will be equal to, we have times 2.18 times 10 to the power negative 18. This will give us a value of 2.0928 times 10 to the power negative 18, like that. So this will be the energy difference. So you can just put energy difference. So this should be the energy difference. So then this question says, a line in the spectrum of atomic mercury has the wavelength of this. When mercury emits a photon of light at the wavelength, at this wavelength, what is the frequency? So using the same simple formula, which is the speed of light is equal to the product of the wavelength and the frequency, we are able to find the frequency. So over the wavelength, the frequency should be equal to the speed of light over the wavelength. So the speed of light is 3 times 10 to the power 8 meters per second. So even the wavelength has to be in meters. So where you see nano is 10 to the power negative 9. Then we have the meter. Instead of writing 254 nanometers, we are just going to, where there is nano, we put 10 to the power negative 9. That's the meaning of nano. That means to say we have converted to meter. So meter, they cancel. Then we just do the math. So we are going to have, when we divide these two, we are going to get a 1.181 times 10 to the power 15. That's the frequency. So our frequency is equal to, we are going to have 1.181 times 10 to the power 15 Hz. Then this question says, why is it harder to explain the spectra of polyelectronic atoms and ions than it is to explain the line spectra of hydrogen and hydrogen-like ions? So firstly, hydrogen only has one electron. So however the behavior of that one electron will be, it will be very easy to scatter. But when we are looking at a lot of electrons, so as we look at atomic structure and periodicity further on, you are going to find that maybe 2 electrons are put in one subshell and other 2 electrons are put in one subshell. So it is very, very difficult. And also electrons, those electrons are able to interact with each other, so which makes it more and more complex. So how are we supposed to answer this question? So let me write it and explain. So this explanation will make more sense as we continue with our atomic structure and periodicity. So we are saying that for hydrogen and hydrogen-like atoms or ions which have one electron, all orbitals have the same value, with the same value of n, which means the same number, the same shell have the same energy. So they have the same energy. However, polyatomic atoms or ions, those that are found many in the shell, also depend on the angular momentum quantum number, of which the angular momentum is more like we are referring to the shape. All this is going to make more sense as we go on, which can repel. So in one shell like that, there are more. There is the S shell, there is the P shell, there is the diffuse dumbbell and all that. So in short, all we are just trying to say is that, let's say for example, to bring it into context, we can have something like this. So all these are holding shells. They are found here. Now due to this, it also depends now on what type of angular momentum are they in. That also determines the energy that they can be able to release. But for hydrogen, they only have one type, which is the S type. So that S type, the same electron will be able to move from one point to another, and the energy is the same across that. So that is why it is very difficult. Now the last thing that I just want to talk about is the fact that how do you know which one will release more energy? So to know which one will release more energy, like for example, if you have 2 to 7, then you have 7 to 2, then you have 5 to 1. My guess here is 5 to 1 will release more energy. Now remember, the Rydberg's constant is common. We know that to calculate the energy released, we said Rydberg's constant times 1 over n1 squared minus 1 over n2 squared, like that. So the Rydberg's constant is common, so we are going to forget about this. So whatever outcome will determine, because if we get 5, we are going to multiply by the Rydberg's constant. If we get 15, we are going to multiply. So whichever one, since this is constant, whichever one has got the highest number is the one that releases more energy. So let's verify. So from 2 to 7, this one is absorbing energy, because an electron, if it is at 2, when it absorbs energy, it will jump like that. It will jump. However, when we look at 7 to 2, this one will release energy because it is from a high energy level to a lower energy level, like that. So it will be able to lose energy. So let's test this. So we are going to have our 1 over 7 squared, but don't care about the sign for when you're doing this. 1 over 2 squared, like that. So what are we going to have? We are going to have 1 over divided by 7 squared, which will give us that value, minus 1 divided by 4. This is going to give us a value of 0.229591. So this is from 7 to 2. How about 5 to 1? So 5 to 1, we are going to say 1 over 5 squared minus 1 over 1 squared, like that. So remember, we don't care about the sign for this one. So we just want to test. So we have 1 divided by 25. So 1 divided by 5 squared is 25. Then we subtract minus our 1. This is going to give us a negative, but we don't care about the negative sign. So we have 0.96. So this is 0.2. This is 0.9. So already that tells you that from 5 to 1, that will release more energy, which makes sense, because if you remember our thing, you will find that the more you go, the more closer the shells become. So the more you approach one, the more energy that is released, as compared to somewhere here. You can even tell the difference like that. So remember, you can have an infinite number of shells over a finite distance, meaning to say over a distance that can be measured. So remember Lyman series, Balmer, Paschen, Brasken, we have the P fund like that. Thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.